Welcome to a new episode of Solar Turbine webinar series. Today, our fantastic presenter, Marutisinh Raj and Benoit Fécamp, will discuss about cogeneration, hydrogen, and carbon reduction, with particular focus on Asia Pacific and India. My name is Emilio Rigamonti, and today I will be your moderator for this session. And I want to thank you, all of you, for spending your time with us, and welcome all of you. I'm part of Solar Turbines since more than 10 years, and I've been living in Asia for more than 5. Before entering into the webinar, let's do a little bit of housekeeping. This webinar will be recorded, and the recording will be available on our website at www.solarturbines.com, where you can also find all our previous webinars and the future ones. As we have seen in the presentation, before entering in the webinar itself, you have seen some questions on the screen. You can answer those questions on the live chat that you see on the right of the screen. There is a link where you can provide your answers, and we will comment the answers with our presenters during the course of the webinar. Of course, you can make questions. We want to make this as participant and lively as possible, so you can make your question in the chat box, and our support team in the background will try to answer you live, or we can address this question to our speakers. Finally, if you have any issue about connectivity, you can drop an email to webinars@solarturbines.com, and our IT support will help you to reconnect. Solar Turbines is the largest manufacturer of gas turbines between 1 and 23 megawatts. We are part of Caterpillar since 1981, and we have installed our units in more than 100 countries. We sold more than 16,000 turbines, and what is very important, we have our service and sales representatives in more than 65 countries all around the world, dealing directly with our customers. Solar workforce is made of more than 8,000 people. What is very important also is our service organization. 2,600 of our employees are working in customer service, and more than 1,000 field service representatives are going every day to our customer sites to support them in the operation, maintenance, and service of our turbines, with particular focus on quality and, of course, safety. What you see here on the screen on the left is our product, a gas turbine package that can be equipped with different type of gas turbines, starting from 1.2 megawatt all the way up to 23 megawatt. Of course, you can use the exhaust of a gas turbine to produce different type of heat. And in this slide, you see an example of the steam that you can generate out of each gas turbine with a moderate post-firing. In the first part of the webinar, Marutisinh Raj will give you a better and more detailed explanation of all the different applications in different industrial processes, and we'll enter in more details with case studies on cogeneration. So let's introduce our speakers. We start from Marutisinh Raj. He's our RSS manager for Asia Pacific Northwest. He has 15 years of experience in gas turbine sales, marketing, and business development. He has an electrical engineering degree from the University of Baroda and one MBA from the same university. He's responsible for sales in India, Thailand, Bangladesh, Vietnam, among other countries in the region. And his fields of expertise are marketing, sales, cogeneration, hydrogen, and clean fuels. The second part of the webinar will be presented by Benoit Fécamp, which is our European Market Development Manager. He has more than 20 years of experience in gas turbines R&D, project management, marketing, and business development. He has an executive MBA from Bocconi University in Italy and a master's degree in energy engineering from INSA Rouen, France. Benoit is our expert for alternative fuels, along with hydrogen, of course, pulp and paper industry, and he has a long experience as project manager. His fields of expertise are decarbonization strategy, syngas, hydrogen, energy efficiency, energy storage, and he will enter in more detail about the opportunity that are present on the market with hydrogen and gas turbines, and decarbonization strategies with particular focus on India. So without further ado, we can start with the first part of the webinar, and I introduce Marutisinh Raj, and you can take it over from here for the first part of the webinar. We'll talk later during the Q&A session.
Thank you, Emilio. So to begin with the first part, I'll cover the topic on gas turbine-based cogeneration plants, how that can help customers and industries reduce on the operating cost with high efficiency and provide a clean and reliable source of energy, helping them reduce the carbon emissions, which with gas, you can see that the carbon emissions will be reduced by half compared to coal. And it can further be reduced with hydrogen fuels or high hydrogen fuels to a negligible level. So the gas turbine range that you can see solar has starts from 1 megawatt, and each 1 or 2 megawatts we have our gas turbines like Centaur 40, Centaur 50, Mercury 50, which is a special gas turbine with very high efficiency, recuperated gas turbine. So every 1 or 2 megawatt we have our gas turbines so that we can select appropriate gas turbine model for the customer needs. The highest gas turbine rating that we have is Titan 250 with 23 megawatt. The steam can be generated from the gas turbine exhaust. It can be unfired, so we can completely utilize the exhaust of the gas turbine to generate the steam or chilling, or in case the requirement is higher, we can do the supplementary firing in HRSG up to 800 degrees centigrade or higher than that, depending on the requirement. The steam can be generated with 1 megawatt, 1.2 megawatt gas turbine Saturn 20. We can generate something like 7 to 8 TPS of steam. So that's entirely depending on the customer's requirement. We can design the plant. So this slide show you the PGM, which is power generation module, specially designed for our power generation customers. The package is plug and play. You can see various parts of the gas turbine package. The PGM 130 is basically power generation module with our Titan 130 gas turbine. PGM 70 is basically power generation module with our Taurus 70 gas turbine. So we have complete range covered for PGM package, which is specially designed in a way that it will take a minimal time at site. The different parts of the gas turbine package, you can see like air inlet system, like package ventilation filter, turbine air inlet filters, inlet fans. The ladders and platforms are provided for the reaching out the difficult places for maintenance. The MCC and on-skid control box is there on the package itself. The enclosure, it is completely enclosed. This is the package exhaust system. The internals of the gas turbine you will see in the next slide. So this is the 360-degree view of the gas turbine package PGM 70. You can see the generator, gearbox, the gas turbine portion. Coming to the alternative fuels that solar can burn in the gas turbine, we have a very wide range of fuels that we can burn, starting from the standard fuels with high methane content. We can burn the pipeline natural gas, which is like typically 80-90% methane, then associated gas, landfill and digester gas or raw natural gases. What solar has specialized is on the different fuels or alternative fuels where we have high hydrogen content like refinery gas or coal and coke oven gas, gasified biomass or waste basis gas. The gases can be burned in the gas turbine, and this can provide power and heat to the customers. Coming to the industry specific solutions, we work with different industries in the market to provide them a solution. It can be simple cycle solution in the desert, providing power to the customer, and it can be a combined cycle solution where a very high efficiency plant is designed to meet the customer's power requirement. The steam turbine can have further bleed or extraction from where a steam can be taken out. The customer can also go for a hot water generation apart from, in addition to the steam. For the specifically like ceramic industry, we have plenty of experience where a spray dryer is used, which is utilizing the gas turbine exhaust to dry the product. The paper tissue industry, where we can go for a conventional CHP, or we can go for a direct drying, where part of the gas turbine exhaust can be used in the Yankee hood, or part of the steam can be used. So in that way, we will have a higher efficiency than the usual CHP conventional plant. We can also go for a generation of chilled water, basically with the direct exhaust of the gas turbine, or we can use the steam generated from the HRSG. So depending on the customer's requirement, we can look at the CHP and we can guide them. This is one example of resilience shown by a gas turbine based CHP plant at our customer installation in USA, where the hospital kept running because of our CHP plant even after the Hurricane Harvey. So this basically shows the reliability of the gas turbine plant and how dependable it is. So coming to the topic, like why the customers should go for CHP, is basically the reason, like energy efficiency with a CHP and the emission reduction benefits. The traditional system will have a grid where a power plant is far away with T&D losses, burning some fossil fuel, and the customer is using a boiler with a gas fuel to meet his heat requirement. So in that way, the traditional system will generate something like 49,000 tons per year of carbon emission. Whereas the CHP system, with the same amount of fuel that we were burning originally in boiler, we can generate the electricity and heat that was required originally, and reduce plenty of CO2 emission. Like CO2 savings will be of the tune of 26,000 with this, and there is a lot of savings on the fuel. So that is also a cost reduction. On this slide, I'm comparing CHP, gas turbine based CHP, with a photovoltaic solar power generation plant and 10 megawatt wind power generation plant. You can see the annual capacity factor in case of CHP and dependability will be very high, because it will be available typically like 85% or 95% of the times, whereas the solar PV or wind based power generation will be having a very less capacity factor. The annual electricity generation in that, because of this reason, will be very high with gas based CHP. The useful heat of gas turbine exhaust can be used in the process with the steam or chilling or whatever the customer need is. In case of the solar PV or wind, we don't have that. The footprint requirement with the gas turbine based CHP is quite very less compared to these other solutions. The annual energy savings will be pretty high. The CO2 savings with the gas turbine based CHP will be 42,506 tons, and in comparison to the other alternatives. So very high value proposition is available with gas turbine based CHP. So now we will take a poll break and Q&A session. Emilio?
Yes, Maruti, thank you very much for this first part of introduction, interesting information. And I think there is more to discuss, but I see some questions already coming in, so let's try to answer some of them. The first one is, I don't have a pipeline gas near my plant. Sorry, the pipeline is not available near the plant. Can I still consider a cogeneration plant with gas? You're on mute, Maruti. You have to unmute yourself. Thank you.
Okay, thank you, Emilio. So the customer where they do not have a pipeline gas, they can go for a cryogenic solution, where a trucking LNG trucking based solution will be providing them the gas fuel for burning in the gas turbine plant. So that's quite possible. There are customers where in a remote area or a difficult places, they go for this kind of solution. It's possible.
Clear. Another question which is coming in is how can we use the exhaust of the gas turbines in different ways? You talk about steam, you talk about chill water. What are the other options?
So we can go for a thermic fluid heating, or we can use the direct exhaust of the gas turbine, like in ceramic we have seen. We can go for partial use of direct exhaust of gas turbine. So it's purely the gas turbine exhaust is purely energy. It can be used in a different ways. It can be used for a chill water generation. It can be district heating. So there are various ways in which this energy of gas turbine exhaust can be utilized.
Yeah, and we see now on the screen the results of the poll that we were putting on the beginning of the webinar. You see, I think the result is pretty self-explanatory. It's very important, the carbon reduction for this type of investment cogeneration. So I think you will give some more information about this in your second part of the presentation, and also Benoit will go even deeper on this topic. So I think we can switch and go directly to the second part of your presentation. Please go ahead.
Yes. So hope you are able to see the screen. We'll start with industry-specific case studies in a different industry type where the energy requirements are different and how they can utilize the gas turbine-based CHP. So the first case is of a chemical plant, a typical gas turbine plus HRSG kind of solution, where the utility requirements are 7.2 megawatt of power and 29 TPH of steam. The electricity cost is considered as 10 cents, and natural gas cost with a long-term gas supply contract around $12 per MMBTU. The plant is continuous operating plant, 8,500 hours per year. You can see the heat mass balance diagram where the gas turbine is utilizing the gas available at 23 bar to burn in the combustor of the gas turbine. The exhaust of the gas turbine is pretty much a lot of energy. So 90,000 kg per hour of exhaust flow and 532 degrees centigrade exhaust. To reach to 29 TPH of steam generation, we will need to do some duct firing. And with that, we are meeting the customer's requirement with a CHP efficiency around 88%. So pretty high efficiency, you can see. The traditional system where grid-based power generation was there and the fuel was burned in the boiler, the annual operating costs were something like 15 millions. With a CHP, we'll burn a fuel in the gas turbine as well as the boiler, and there will be a maintenance cost related to the CHP plant. So that will be something around $12.7 million US. Net savings you can see in the graphical form, and the calculation will be something around $2.6 million US, and the amount invested and the maintenance cost altogether, the payback will be something around 3.4 years. So pretty solid payback for the customer. The second case I will present is of a tissue paper company with a production capacity of something like 30,000 tons per year. Power requirement is assumed as 10 megawatt and steam requirement is 20 TPH. The utility costs are considered as 10 cents and gas price is $9 per MMBTU. Just some background about the paper tissue industry. So the roll typically weighs around 100 grams each roll. The utility average requirement are to produce that roll are something around 90 watts of electrical power, 205 watts of thermal energy is used. In Europe or US, you will see typically the carbon emission of 80 grams of CO2 per roll will be emitted. Whereas in case of Asia, China, Africa, Middle East, you will see 120 grams of CO2 emitted per roll. So likewise, in 2020, you will see 1,000 billion rolls were produced. So you can imagine the amount of emissions in that situation. So in case the customer has no cogeneration plant, you will see the operating costs for producing this many tissues will be around 14.9 million US dollars, and the carbon emission will be around 84,000 tons of CO2. If we go with the GT plus HRG conventional solution, will reduce the operating cost by 11.4 million by 23%. So it will be 11.4 million US dollars. The emission CO2 emission will reduce by 33%, and we can increase the efficiency even further and go for direct drying. So there a partial gas turbine exhaust will be used and partially the steam will be used. In that way, the plant will have much higher efficiency. So OPEX will reduce, like 10.9 million will be the new operating cost, 27% reduced from the base case, and the carbon emission will reduce further from the base case by 38%. So GT plus HRG steam only solution or conventional solution when compared to no cogeneration plant will have in this case something like 4.5 years of payback. The annual money saved will be something around 3.5 million US dollars, and CO2 emission will be reduced by 26,000. The direct drying will be further effective with a payback of 4 years, and savings increased to 4 million US dollars and CO2 reduction around 30,000. The third case is of emerging industry hyperscale data centers. The ambient condition that we have taken is around 30 degrees centigrade when we want a power and chilling for the CHP plant. The utility cost we have considered of a commercial electricity cost of 12 cents per unit and gas cost of something around 12 US dollar per MMBTU. Just to give you background, the traditional data centers that we have compared here consumes power coming from the grid to meet their requirement in the IT center, the data center in their utility requirement. The part of the power consumed will be in electrical chillers to generate the chilling required for the data center. Compared to that, if we go for a gas turbine, we can burn the gas fuel or a different fuel like hydrogen. So in future, we can go for hydrogen fuel if we want to completely decarbonize that. So with gas turbine, we can generate part of the power requirement for a data center. Part of it can come from grid. And then the gas turbine exhaust can be utilized in the absorption chiller, generating the chilling amount required for the data center. This way, because of its high efficiency, we will reduce the PUE. The typical CHP efficiency you can consider around 80–90%. The payback will be around 4.5 years, and it's a reliable source of power with redundancy. The savings per year for customers will be around 9.5 million US dollar, and there will be a lot of savings in terms of carbon emission, 160,000 tons we can save. To summarize the benefits of CHP, the CHP with a gas turbine is much more efficient than conventional solution where we go with a gas turbine based electricity, the grid supplied electricity and a separate boiler where we burn the gas fuel or coal to meet the thermal energy requirement. Because of the high efficiency of CHP, the operating cost will be pretty lower. The emissions can be pretty low compared to the coal or any other type of conventional plant with burning the fossil fuel. We can go for a particular selection where we can look at the environmental regulation of a particular country, and we can meet the requirement of the country. So our gas turbine package can comply to the local regulation. The CHP plant will be a dependable, reliable source of energy with the quality of power and resilience that it provides as a plant. The on-site electricity generation basically reduces also the grid congestion, and there are no T&D losses because we are using the captive power generator for the use of industry. That's it from my side, and we can take a poll break and Q&A.
Thank you, Maruti. Yes, definitely much more information in this second part, and I think the outcome of this presentation is that there are not just benefits in terms of economics, but also in terms of emission reduction. Very, very interesting. And this is just using pipeline gas. So we will see in the second part how can we further reduce these emissions. But before getting to the second part of the webinar and introduce our second presenter, there are some questions about the price of gas. You have shown different price of gases in your case studies. The question is, how can I address the risk of gas price fluctuation? Because we know the price market is quite volatile, maybe particular reference in India. How can we answer this?
So basically, the customer can go for a long-term gas supply agreement with the supplier, like GAIL or any other local supplier that they have. There are LNG terminals supplying the cryogenic solution. So this way they can control the cost of gas that they spend on the operating cost. So there are a lot of options like that available. So long-term agreements will reduce their operating cost and safeguard them against any peaks of a gas price that we see right now.
Yeah. And the other question is about emissions. So there are customers that are currently using coal and they want to switch to gas. How this is compared to the situation, the case study that you presented? Is it better in terms of emission reduction if they switch from coal to gas?
So switching from coal to gas has a direct benefit in terms of CO2 emission reduction, like it will be reduced by half. And what we are doing is we are looking at using the high hydrogen fuels, like my colleague Benoit will present that in detail. With that, the emission can be further reduced. So there are definitely benefits. And in India, probably the carbon credit mechanism, selling of the carbon credits is not very active. But with that, the benefits will be even higher for the customers.
Clear, perfect. Well, so let's see how much we can push this even further with hydrogen and carbon reduction solutions with the second part of the webinar. So Benoit Fécamp will introduce you the second part, and I hand it over to you, Benoit. You can take it from here.
Thank you, Emilio. Thank you, Maruti, for the very interesting presentation. And indeed, we'll talk about the carbon reductions in this very part of the presentation, what we can do today, and then we'll look a little bit in the future with hydrogen and other gases. So let's start with these decarbonization strategies. Let me put my pointer as I do. This is a first slide looking at the CO2 emissions from fuel combustion by sector in 2018. It didn't move that much, so we can look at that. This is by sectors. Interesting to see that the electricity and heat production is by far the largest contributor in terms of CO2 emissions in the world. So we'll dive a little in this sector now. So we talk about fuel combusted. So interesting to understand is that if you combust various fuels, you will have various CO2 emissions. Even to produce 1 kilowatt of energy, you would produce different kilogram of CO2 if you burn different fuels. So looking at this table on the top right, you see, for instance, coal. You would produce 325 grams per kilowatt hour of CO2, while with natural gas you will produce only 181. So let's look at just the fuel switching. So from coal to natural gas, already you would reduce your CO2 emissions by 80%, and just doing that using the same technology. So indeed, we talk about fuel switching, but we need to look also at how heat and power is actually made, because it can be done in different solutions for a plant. So let's look at that. And Maruti already talked a little bit of that. I will repeat because this is very, very interesting. This is an example of a plant. It's an exercise with a 5 megawatt electrical and 12 tons of per hour of steam need. And if the plant is using the grid, the grid itself will actually need some to produce electricity. So it will need, like for a combined cycle, you would need 11.5 megawatt to produce this 5 megawatt of electricity. For the steam, you consider a boiler, and then for this 8 megawatt, you need 10 megawatt of fuel. For total 21.5, comparing to a combined power, in this case with gas turbine, 5 megawatt natural gas fired, you would need only 17 megawatts. So you see easily the nice fuel utilization improvement. Just let's say choosing the way you produce electricity and heat. So on site with CHP and importing electricity and a boiler. Of course, with this fuel utilization, you have improvement in CO2. With the same gases on both sides, you would have 21% improvement and 25 tons per year in this case. But if you move from coal on this side to natural gas, it's even better. We understood from fuel switch, CHP now, and then we look exactly at what are the results if you put in place this this strategy. So let's look at this switch from coal to gas and CHP in particular. This example is another theoretical plant, let's say needing 1 megawatt electrical and 2 megawatt of steam. Of course, it's the same for 10 megawatt electrical or 20 megawatt of steam, just multiply. And this plant led for India, so would import electricity from the grid. And so the grid has a certain CO2 intensity because there is a certain amount of coal, diesel, wind, etc. That's used to produce the power on the grid. And then the plant would use a coal boiler to produce the steam. The CO2 intensity of this plant will be actually 450 grams of CO2 per kilowatt hour. If you look at this nice purplish bar, which is a CSP natural gas fired based on gas turbine, you see that you will be right under 200 grams per CO2 per kilowatt hour to produce the same power and heat. So you see there is a very nice opportunity there for more than 50% improvement in terms of CO2 footprint moving to natural gas fired CHP. So it's very interesting opportunity. Of course, if you have more important objectives, so going to maybe 100 grams of CO2 per kilowatt hour, or even zero, if you can have objectives, then you have other solutions you need to put in place. Carbon capture, we'll not talk about that today, but it's a solution. Biofuels, we look at that a little, and green and blue H2. Indeed, let's look at the color of H2. I think it's important to talk a little bit about that. H2, if you don't know, is a colorless gas. And when we talk about the color of H2, it's just a way to explain and to memorize how the H2 is produced, actually, in terms of CO2 impact. And we look exactly at that now. Here are a few colors. You see brown, gray, blue, and green. There are various other colors that we are talking in the news now, pink, turquoise, yellow, but those are the major ones. Brown and gray, those are the typical way H2 is produced today. So it's from coal or natural gas. You produce H2 and CO2. Then you have the blue hydrogen, which is the same processes, but you add a carbon capture equipment at the end of the process. It's low carbon because both processes do not capture 100% of the CO2. It's 95 now, we can see. So it's still low. So this is some CO2 emitted. And then we have the zero carbon, and typically that's the green hydrogen we're talking a lot in these days. And apart from some niche product, green hydrogen is mainly renewable power, feeding an electrolyzer, so electrolyzing water, producing H2 and O2 as another of gas. So what does it mean in terms of decarbonization or decrease of the footprint when you use those gases? So we talked about biogas and biodiesel. and H2. We have this nice graph on the right-hand side to help understand the impact of a blend of biogas and with natural gas or H2 with natural gas. For instance, if you look at this axis here, 20% would be the amount of H2 in the gas, the rest will be natural gas. So for instance, 80% here, if you look here, would mean 50% reduction. 80% H2, 50% reduction in terms of CO2. Interesting, and do the same with the biogas with the blue line. So what we can say for biogas, interesting thing, which is available today, the gas itself, limited availability in the sense that it's not that easy to find enough gas to feed a large turbine, like 25 megawatt, but it's definitely possible to feed a 3.5, 4 megawatt machine. Solution technology exists for the gas turbine. Let's say you can inject 20-30% of biogas in a solar NOx, so a DLE for solar, or even 100% in a conventional, so would be almost zero CO2, biogenic CO2 actually. So intrinsic cost, because most of the time it's let's say it's off gas of agricultural waste on site. H2, so we talk a lot about it today. Of course, low or no carbon, and limited availability today. We see that in India, but it's the same around the world. The interesting thing is that there are large plants, large potentials for very large volumes. So that's the interest here. Costs today are pretty high, or I would say even very high, but again, with the large volumes, there is a good or very good potential to go low and be competitive. Indeed, I mentioned that a little bit. Let's look at India a little bit, what is happening. Let's start with the Prime Minister Modi. So that's announced in the India Independence Day on the 15th of August, the hydrogen mission. And there are a few things that are very important. So the vision to have India as the global hub for green and hydrogen production and export, import of H2 for India Energy Self-Reliance, and a few proposals that are very interesting also. This is the idea to make green H2 mandatory for fertilizer plants and oil refineries. Those industries are the ones that are using the most hydrogen today, but gray and brown. So it's very interesting here. And then based on that, we increase of volumes, decrease of cost, and the plan to have production-linked incentives. On looking at projects, interesting first is the Acme Group or CME that commissioned the first green H2 plant, so in Rajasthan. And then you have recently some project has been announced, GSW Energy, Indian Oil, BGR Energy, and the new India Hydrogen Alliance have been started, led by Reliance Industries. Emilio, if it's time for a port break or some questions.
Absolutely, thank you, Benoit. Very interesting introduction on the hydrogen capabilities and decarbonization. And I think one of the questions that is coming in is what is the difference between a gas turbine which is burning hydrogen and the one which is burning natural gas in terms of efficiency, for example?
Well, that's interesting question indeed, because some of our customers that are familiar with other technologies tell us, well, you will have less power, you will have less efficiency, and actually, a gas turbine is not the way it works. Nice thing with hydrogen and gas turbine, you will have the same, almost the same, because we talk about 0 point something difference, but same power, same efficiency, it's same heat available for your process. So no real difference in terms of performances against other competitive technologies.
Very good, very good. As I usually say, gas turbines likes hydrogen, so it's a good fuel. Perfect. So we see here on the screen the result of a poll that we had in the break. So this is a projection of how many percentage of hydrogen our customers are expecting to use in the next 10 years. So I think there is maybe an idea of progression, so starting with a lower percentage and then going higher, but now we see live that the 50% is also going high. So maybe are the two different applications. So I think that the above 50 are more the 100% hydrogen for fertilizer. So any comment on this?
What's interesting, maybe we can cover that in the next slides, but indeed there are different technical solutions for both, let's say, the low level and higher levels. Maybe the over 50% could be on some other gases that we will talk about. Let's see. I hope we can let's say feed the curiosity of our attendees.
I'm sure you will. One more question before we get into the second part is focus on India actually. So we see that hydrogen is not available in large quantities in India right now. What are the opportunities for low carbon aside from hydrogen?
Yeah. In fact, it's a question, but a bit, let's say, on the mouth of our customers. What do I do if there is no hydrogen? But for India, I think that I try to emphasize that, but there is a large opportunity with natural gas-fired CHP. I tried to explain that more than 50% CO2 footprint reduction. Lots of countries would love to have this opportunity, but also, as I said, biogas, which is can be available pretty readily, even if not that large amounts, can make a difference in terms of CO2 emissions. So I would say CHP and biogas for carbon reduction now.
Clear, very clear. Thank you. And you can proceed with the second part then. Thank you very much.
Let me it like this. Okay, Emilio, so that's the second part I wanted to share with the attendees, our capabilities, because that's important to understand if you want to invest what we can do. Let me try to move my slides. So it kind of shows also what the customer was saying before, or the attendees saying before, below 20%, over 20%, and that's interesting to see that we see also this difference. We see two markets. So the pipeline gas applications, where we see that the hydrogen could be transported in pipelines, and this threshold that we see as a technical consensus worldwide is that over 20% the users of the gas, but where the hydrogen would be blended, would have too much cost to upgrade their equipment. So the threshold in the pipeline applications will be 20%, as we see it. And what we propose to the market for this 20% is the solo NOx or DLE combustors. On the right-hand side of the slide, we see the industrial processes. And there we see hydrogen content that are far over 20%, 40, 50, 60, 80, even 100%. And that's where solar turbines is very strong. And we see in some next slides some application in terms of steel industry, in terms of refinery of gases. And we still see picking up some interesting new applications regarding gasification to energy. So a bit busy slide, but I will not go too much in detail. This is the Solar's hydrogen technology experience. On the bottom, you have the conventional combustor. And on the top, the gray line, the gray bar maybe, is the dry low emissions combustor. Let's start with the conventional. So the solar turbines hydrogen journey, I would say, started in 1985 with a machine that was already running at 40% hydrogen. And this is the refineries. It's still been running today, even if not so refurbished and new engines, but still the same location with this of gas. Looking at conventional, I would highlight the 2005 first 60% H2. This is in the coke oven gas industry, the steel industry. 2018, on the same market, we reached 46 units installed. And 2021, this market has over 2 million operating hours, which is really a huge experience in terms of H2 understanding, in terms of equipment, and no other OEMs are able to show those kind of numbers and experience. Looking at DLE, the DLE was introduced in 1989, and already in 2003, the first Titan 130, which is a 15 megawatt machine, was tested at 15% H2 and has been running since at 9% H2. Going at the end of this slide, so today we're able to deliver DLE at 20% H2 capability. Summarizing our capabilities in terms of products, light blue This is the range of product. The light blue bars are the capabilities in terms of diffusion flame, in terms of conventional combustor, as we call it. And the dark blue is the DLE, or our names for Solenox. Most of our engines, you see, are able to go 100% in conventional and 20% in DLE. Of course, those limits are not written in stone. It's definitely based on the market demand. And what we see in solar is that the market will very probably request 100% H2 DLE around 2029, 2030. It will be based on how much production of H2 is available, really, between H2. And so we developed a roadmap to reach this 2030 with 100% H2 DLE. Of course, if the market demand accelerates, we accelerate the roadmap as well. Okay, I wanted to finish on that on some case studies on hydrogen-rich fuels and off gases, because it's an opportunity that is, I would say, often not captured. And the idea is to stop using these off gases in boilers to produce steam and low efficiency electricity, and try to use far more efficient solutions like gas turbine CHP and gas turbine based combined cycle to reach very high efficiency. And that's what we'll see. So this is an example of the PDH plant, a propane dehydrogenation plant. This is a process that takes propane to produce propylene directly, and out of this process, if you know some chemistry, there is H2 that is going out of this process. So H2 is naturally an off gas of this process. Sorry, and this plant is pretty nice. It's a Titan 130, so 15 megawatt based CHP, so combined and power with a heat recovery steam generator, 2 pressures, using SCR for low emissions, so reaching even 25 ppm NOx. So it's very interesting. The off gas used is over 80% H2. And what interesting feature, or very interesting feature of this plant, is that it is able to run at 100% natural gas, at full load, which is normal, you would say, but also switching to 100% of gas, the one that is 80-85% H2. So staying at 100% load, power and heat. So you can switch fuels even at full load. This is very nice for the customer. So reducing flare operations, reducing CO2 emissions, and having a very good return on investment due to the use of efficiency solutions like this one. So happy customer. Nice one, and last one for the case study is the example of the coke oven gas industry. I said before we have more than 2 million operating hours on those applications. The plant we are showing here is the 4.4 pair Titan 130 gas turbines. It's a 55 megawatt electrical plant, and very efficient, more than 80% thermal efficiency for this plant here. Again, using a gas that is between 55-65% content of CO, high level of contaminants, so very interesting applications. Let's conclude and maybe discuss with some questions later. What we saw with this presentation is that gas turbine-based CHP, even with natural gas, enables strong carbon reduction in India. So we have the first question before, but also biogas can help decrease even more the CO2 footprint. And then we see also in the future that hydrogen will also help to decrease this CO2 footprint as well. Solar has a very large gas turbine fleet running on hydrogen-rich fuels. You saw that solar gas turbines and packages, we don't see compressors, but tell you now, are hydrogen ready now. And with the roadmap that I did show you, solar is continuously increasing investment in the hydrogen solutions. Okay, Emilio, that's it for the presentation. We have probably some questions.
Yes, absolutely. We are responding all the questions coming live in the chat. So I think we are covered for now for that, but we have some others coming. So let's take this one. I'm considering to purchase a cogeneration plant. Shall I wait till the hydrogen will be available, or and hydrogen ready turbine? Or can we install a cogeneration plant? Maybe I think the question is, can I install a cogeneration plant running with gas now and ready in the future to run with hydrogen?
Yeah, I think I could spend 30 minutes just on this question.
We still have time, so 10 minutes, not 30.
I will focus just on maybe a technical piece, because already on the investment side, I would say since there is a good return on investment today, I think you should invest as soon as possible to capture this value that you might not have tomorrow. So I would just say on this side. But on the technical piece, I think there is no issue. At least the industry doesn't see any issue. We'll not even talk about solar turbines alone. The industry has seen in the past the move from diffusion combustor to Solenox, to DLEs, to low emission combustors, and it went pretty smoothly with the gas turbine that was due to overhaul, that has been exchanged with from a diffusion flame to a new DLE combustor and new DLE gas turbine, and with a small upgrade to be done on the gas turbine. So there is really not very issue there. When the H2 will be available, the gas turbine will be exchanged at the overall time with a hydrogen ready gas turbine, and with a small upgrade, the package will be running with hydrogen fuels. It's no issue there.
Yeah. So I think this is also answering another question, which is asking, can gas turbine run with both natural gas and hydrogen? So can we switch between the two?
Yes, we can. Indeed, if in the case study I presented, it was off gas. We could switch from natural gas to off gas, but it's the same with 100%. So you could eventually, even a 20% or 40% blend, you could switch from both gases without any issue.
This is a more interesting, I think, for many question, which is about capex and opex. Is a gas turbine capable to burn hydrogen more expensive in terms of capex and opex? Give some.
Yeah, I think if you want to invest, it's a fair question. Capex, I would expect some small differences, indeed, because H2 in the gas requires that you change quite a few things, like instrumentation, like a class of the equipment, C class, for instance, the class of the gas. You need to potentially increase your firefighting capabilities. So there are quite a few things you need to add, to change. There will be a small amount in terms of capex. I would say not super significant, but still a small amount. In terms of OPEX, that's the other nice thing. You don't have to expect any change in terms of OPEX for a gas turbine, fired gas turbine. Natural gas, no, sorry, hydrogen fired gas turbine, sorry.
Clear. I think this is a question that is coming from many angles, so it's very important to answer. And finally, since we have 5 more minutes, can you explain how Solar is positioned in the hydrogen market in terms of capabilities and what is the future? How we are planning to adjust our products in the future?
Yeah, okay, that's also a long question potentially. I would say a few things. So if we kind of summarize, there is the hydrogen market today that is driven by off gases, because that are rich in H2, because the green H2, as we saw in India, is the same everywhere. Green H2 is available almost nowhere. It's just in very few amounts on pilot plants and nothing industrial. So the hydrogen market today is on off gases. And solar turbines is extremely well positioned there, as I explained, with the Cocovan applications, with farm applications in our class side, from 3 to 23 megawatts, reaching the emissions of the market, so 25 ppm, even less some occasions. Then when we look at what the market is starting to ask, and that's a bit coming from the question that was answered in the poll. We start to see two diverging, maybe not, but two separate markets. This transport in the pipeline, which is 20-ish % H2 in the natural gas, And Solonox is well positioned there because we offer the DLE for these applications, because typically those are the ones that would be using the gas that are using today. So the gas turbine is already a DLE, and it will be replaced with a DLE with 20% capabilities, which is, as we saw before, available on most of our engines. And then the market of H2 will increase, probably not from 30-40% in the pipeline, but we switch directly to very high amounts, probably 100% directly. And then you can imagine that the market will be the industries will be fed directly with pipeline with 100% H2. It is not tomorrow. We talk about in 10-15 years in some special locations, probably close to the where the hydrogen will be produced. And then at this stage, you would probably need DLE combustors. That's exactly the fault of solar turbines. But envision this need in the future around past 2030. And that's the reason why Solar Turbines is developing the DLE for these very applications, and exactly for those dates. So around 2030 to have available this DLE or Solonox for these kind of applications, 100% H2. Well, I hope I answered the questions, Emilio.
Absolutely, and maybe we can also go back to Marutisinh Raj for final closure on this hydrogen future in India. So I think going back to one of the questions we had from the attendees, which by the way are very active in the chat, and we thank them. So our customer in India, do they need to wait for hydrogen to be available, or they can benefit of carbon reduction and economics benefit right now with just going with gas? What do you suggest?
So my suggestion to the customer who is planning for burning hydrogen fuel in future will be, they can go for the gas turbine based on the natural gas or whatever high hydrogen fuel they have as of now. They can burn that gas turbine. In the gas turbine, we can provide the package for that. And in future, when they have a more high hydrogen fuel or 100% hydrogen available, at that time we can do the necessary changes and they can burn that and switch to basically go for a complete decarbonization in that situation.
Very clear, very clear. So I think we try to answer all your questions. If not, we will definitely come back to you if you left your indication and your address in the chat, and we will reach you out also thanks to the registration. Again, thank you very much for being so interactive, and I really appreciate, we really all appreciate this. If you need to know more, you want to know more about our solution, you can reach us at the email address that you see here in the slide, infocorp@solarturbines.com. And please go on our website. I've seen question asking if there is any information documentation on hydrogen. On our website, you will find our capabilities, case studies, white papers, and you can follow us also on our social media. Thank you very much again, and I hope to see you soon in the next episode of Solar Turbine webinar series. Thank you again, and have a good day.
Thank you.
Thank you.